Our modern astronomy is based on this book, published by Copernicus in 1543. Copernicus realized that the sun is actually the center of what we now call the solar system.
Energy from the sun, in the form of light and heat, supports almost all life here on Earth. But how does one study something that is over 150 million kilometers away?
We start by using from what we can see from Earth, just as early astronomers like Galileo did. Here we can see the moon from Galileo's Sidereus Nuncius in 1610.
One of the most striking and informative solar phenomena visible to the naked eye is a total eclipse of the sun. The moon is 400 times smaller than the sun. Coincidentally, it is also 400 times closer to Earth. When the moon passes centrally in front of the sun, the surface of the sun, or photosphere, is covered almost exactly. This produces a total solar eclipse. Such eclipses cross the Earth's surface in narrow bands, usually not more than a few hundred kilometers wide and at intervals that average 18 months.
The first such plot of a totality path across the Earth was done by Edmund Halley in 1715.
To see every eclipse, one would have to travel widely. A given location on Earth gets a total eclipse once every 300 years on average. During an eclipse, when the moon barely covers the photosphere, the last bit of sunlight can be seen shining brightly through a valley at the edge of the moon. This is known as the diamond ring effect. After the initial flash, we briefly see a reddish band around the sun, known as the chromosphere. Sometimes curvy red shapes called prominences stick up from the sun. When the diamond ring disappears, the solar corona can be seen. The corona, named from the Latin word for crown, is visible for seconds, or sometimes even minutes. From studying total solar eclipses, we learn how magnetic fields hold hot gases in place, helping to provide a key to reproducing nuclear fusion here on Earth. We also learn how the solar wind, the expanding gas that envelops the Earth, is formed. One type of eclipse research studies how the corona gets heated to temperatures of millions of degrees, a process that also heats the coronas of billions of other stars. Total solar eclipses will be visible from the United States in 2017 and 2024. Sometimes the moon is farther than average from the sun, and a ring, an annulus of ordinary sunlight, remains. We call that an annular eclipse. Annular eclipses are visible from somewhere on Earth about as often as total eclipses are. Eclipses are a spectacular, although infrequent, phenomena. So how does one study the sun otherwise? One can study the electromagnetic emissions of the sun, making up gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves. To study waves blocked by the Earth's atmosphere, such as X-rays and gamma rays, one must use special telescopes that are located in space.
The key to studying the sun has long been its spectrum. This is what we see when we break down the sunlight into its constituent colors, its rainbow.
In 1814, Joseph Fraunhofer made the first spectroscope that was precise enough to study these colors in detail. He noticed dark gaps in the solar spectrum. These gaps are now known as absorption lines, or Fraunhofer lines. Fraunhofer lines tell us about the different elements that make up the sun. Some of the absorption lines are darker than others. Fraunhofer gave the darkest ones the letters A through H.
The strongest lines in the visible part of the spectrum are the H and K lines. K was named later, which comes from ionized calcium gas in the outer layers of the sun. The line Fraunhofer called C comes from hydrogen and now corresponds to the H-alpha line in the red part of the spectrum.
Through the use of filters, one can isolate the H-alpha frequency. Using this filter, the chromosphere can be observed, which is normally visible only during an eclipse. The chromosphere is also visible through filters that isolate the H and K lines of ionized calcium. The chromosphere reveals much about the magnetic activity of the sun. Visible are sunspots, regions where the sun's magnetic field is strongest. These appear as dark spots in visible light or white spots in H-alpha. Compared to the magnetic field of the sun, these sunspots have fields that are thousands of times stronger. They wax and wane with a period of about 11 years. In 2009, there were days with no sunspots on the sun. By comparison, in 2013, there were days with dozens of visible sunspots. Professional astronomers use advanced telescopes to study the chromosphere in detail. For example, the ATST, or Advanced Technology Solar Telescope, being built in Hawaii, will be able to collect more light from the sun than ever before.
Special solar telescopes either have filters that drop the intensity of sunlight down to a level that makes it safe to look at, or simply project the image onto a piece of paper, then we merely look at that piece of paper.
One should never look directly at the sun. Your eyes will be instantly damaged if you look directly through telescopes or binoculars. As mentioned before, because the Earth's atmosphere blocks some frequencies of electromagnetic radiation, telescopes in space are also used to study the sun. A major solar telescope in space is the Solar and Heliospheric Observatory, or SOHO for short. It was launched in 1995 as a joint project through NASA and the European Space Agency. SOHO carries 12 different types of telescopes. One type of telescope, known as a coronagraph, creates artificial eclipses. The coronagraphs capture images of the solar corona hourly and show eruptions called coronal mass ejections. SOHO has two coronagraphs, one for the middle corona and one for the outer. They both leave a donut-shaped gap around the photosphere. This is the region that can be studied by ground-based solar eclipse expeditions. This coronal image filling the donut gap is from the 2012 total eclipse in Australia. SOHO also has a telescope that captures images far into the ultraviolet spectrum. The Extreme Ultraviolet Imaging Telescope, or EIT, captures images through 4 filters. These correspond to high-temperature radiation from iron or helium atoms. These filters are used to capture the chromosphere and corona. This clip was taken from a spacecraft launched in 2006. The spacecraft is one of a pair known as STEREO, as they move around the sun at positions ahead and behind the Earth. This enables them to capture stereoscopic images of the sun. Using this, we can capture the back of the sun, which is the side not facing Earth. We can now know which sunspot groups come around to our side. By also studying solar seismology, we can determine the sun's analogy to earthquake waves. Here, the visible light captured through STEREO's coronagraph are patched together with a view from its ultraviolet telescope and are given false color. Notably, STEREO was further from the moon than Earth, so when an eclipse occurred, the moon appeared to be quite small in comparison. Here's the eclipse against the background of ultraviolet images on which you can see solar activity and the sun's rotation. Far away from us is the planet Venus. From our perch on Earth, it passes the sun only twice every 100 years. It takes 6 hours for Venus to cross the sun. These transits of Venus are local analogs to transits of exoplanets, distant planets becoming silhouetted against their distant stars. Massive ground-based telescopes capture enlarged views of the sun. In 2012, one of them showed this view of Venus's atmosphere bending light towards us at the beginning of a transit. Thousands of transiting exoplanets are now known. The next transit of Venus visible from Earth won't be until the years 2117 and 2125. In addition to color and spectra, the motions and activity of the sun are of great scientific importance. Since 2010, NASA's Solar Dynamics Observatory spacecraft has been imaging the sun's surface, detailing phenomena such as solar flares. Such flares can send particles out into space and even cause blackouts in power and communication systems on Earth. The finest resolution images now available are with telescopes on a Japanese spacecraft called Hinode. Like STEREO, it was launched in 2006. Hinode captures details 2.5 times finer than the Solar Dynamics Observatory, though over a smaller region at a time and at a slower cadence. Footage from Hinode can capture spicules, which are fine details within the chromosphere. Spicules rise and fall with a period of around 15 minutes. Hinode also captures solar prominences held aloft over the sun by its magnetic field. Here is a region around a pair of sunspots, including the surrounding salt and pepper effect from convection known as granulation. Hinode also has a telescope that captures full disk images of the sun's X-rays, which do not penetrate the Earth's atmosphere. Hinode can also capture partial eclipses. Sometimes useful observations are obtained from rockets during the 5 minutes that they are above the atmosphere. In 2012, a NASA rocket called HI-C carried a Smithsonian Astronomical Observatory telescope that sent down images of the sun that were about 5 times finer in resolution than the Solar Dynamics observatories. In 2013, NASA launched a spacecraft called IRIS, the Interface Region Imaging Spectrograph, from a high-flying airplane. IRIS contains a high-resolution spectrograph. We have come a long way in solar studies since Galileo and others discovered sunspots in 1610. Now, through the use of spacecraft, we learn about the sun's activity and effects on us with more frequency than ever before.
Entre ser y no ser, la hierba titubea, los elementos se aligeran, los contornos se esfuman, visos, reflejos, reverberaciones, centellar de formas y presencias. Niebla de imágenes, eclipses. Esto que veo somos. Es